Good afternoon and welcome to this week's joint astronomical colloquium. It's a special pleasure to welcome Sadegh Khochfar, who many of you know. He will be speaking about the cosmic nursery, growth spurting baby galaxies and seed black holes, an interesting combination of words, and we shall soon learn what it means. A few words on the speaker. As I said, some of you may know him because he did his study here and his PhD here, just like me, the same group. Then he moved to Oxford with an Otto Hahn Prize from the Max Planck Society. After that, he decided to come back to Germany, and he got a Max Planck Junior Research Group at the Max Planck Institute for Extraterrestrial Physics in Garching, and he did that so successfully that he, after a few years, went back to the UK, and he's now full professor at the University of Edinburgh at the Royal Observatory. Okay. So, Sadegh, welcome.
Thank you very much, Ralph. Well, thank you very much. Let me first thank you for inviting me to come here. It's really a great pleasure being back in Heidelberg after so many years. I still remember sitting there in the back row, listening to my quantum mechanics lectures and thinking, wow, steep hill. Anyway, so before I start, let me just apologize. I mean, the few clouds that you see out there, I brought them along from Edinburgh. So I thought it would be good to have a little bit of a... Oh, well, let's see. Well, as Ralph already told you, I have a quite mouthful for a talk title here. The Cosmic Nursery, Growth Spurting Baby Galaxies and Seed Black Holes. So what is it that I really want to talk about is, well, we all know JWST, hopefully, cross fingers, is going to come up in 2018. And once it comes up, it will be a unique opportunity to probe a region in time where we up to now didn't have much information about, which is what I call the cosmic nursery, a region where the first stars and the first galaxies and first black holes formed. Now, you might say, well, okay, that's interesting. Obviously, we want to know also about galaxy formation. So if you look at it, this is quite a small period of time versus a very long period of time. And even though JWST will go up, you probably will never achieve the quality in data. So, okay, that just died on me. That you will have in the low redshift universe. And I obviously will agree. So, but there's one thing which makes it actually quite interesting to look at the high redshift universe from an observational standpoint. So you can do galactic archaeology by looking at the stars in the local universe and measuring their ages, their metallicities, their masses, etc., and get a very good idea of what you find right now in the galaxy. However, given that there's the so-called star formation main sequence, which is more or less a linear relation between the star formation rate and the stellar mass, you're actually not able to say if all these stars formed in one big progenitor at early times, or maybe in 10 smaller ones, because all of them will lie on that same relation, on that star formation mass relation. So you could, in principle, generate the same amount of stars at a given age, let's say at a high redshift here, just in 10 small ones or in one big one. So you don't know really anything about the progenitor. So that's actually an important reason why you would like to look at the high redshift universe to understand galaxy formation as well better. Now, from the theoretical sides, there's a number of considerations why actually the high redshift universe would be a good place to look for galaxy, to understand galaxy formation in a better way. So one is, well, background cosmology. Now, what you see here is a recent plot by Alan Heavens in which he shows you the base factor, basically, or the likelihood of different cosmological models using the available data. And you see flat lambda CDM, top set chart, and all of these are shown in respect to the flat lambda CDM model. So if you assume that more likely we live in a flat lambda CDM model, then you know how the energy, the matter density scales back in time with scale factor. It's basically the local one divided by a cube. We know that the energy density in a cosmological constant is basically always the same, going back in time. Now, as a consequence, going to large redshifts, or small a's, matter density will very much dominate every energy density in the universe. Well, the energy density definitely with respect to the cosmological constant, and the evolution will be more or less Einstein de Sitter. The nice thing about that is you don't need to worry about cosmology then anymore. You can focus on galaxy formation because you say, well, at high redshifts anyway, everything will evolve according to Einstein de Sitter universe. Now, going back in time, some other things happen as well. So if you look at the dynamical time of an object, for example, a galaxy, and say in first order, the dynamical time of a galaxy scales with the dynamical time of a halo. If you go back in time, then you see, well, the dynamical time usually is 1 over the density, square root of the density. So you can work out how the dynamical time might scale, and you can see that basically from redshift 0 to redshift 6, the dynamical times become short, much shorter than today. And the advantage of that is, if you think about galaxies and galaxy formation as a very simple equilibrium back on the envelope calculation, and you've heard of all these bathtub models. So all they say is, well, the change in gas mass or star forming ISM is whatever you accrete onto it. Let's say I assume that's constant with time, minus whatever you form into stars, minus whatever flows out due to feedback. Then you can write that basically down, and this is a nice differential equation that can be solved easily. And this is just a solution of it, where this is the dynamical time. Now what's interesting is, as I told you, going to high redshifts, dynamical time becomes short. As a consequence, you can forget about this exponent, because if this becomes short, that becomes large, and the exponent basically disappears, and you go to an equilibrium solution for the amount of gas that you have. So short dynamical times allow you actually to have some kind of equilibrium solution easier, and that's much easier at early times in the high redshift universe. Now the other argument why things become easier at early times is that the cooling times just become shorter. So radiative cooling times of gas, again, just basically go like 1 over the density of the gas. And you can just work it out if you just look at the cooling time, saying, well, that's nothing else than the ratio of the energy in your gas divided by the energy loss rate, radiative loss rate of that gas. And just write it down like that, assuming a cooling function. And here you see a plot by Decker and collaborators, in which you can ask yourself, well, if I look at a halo of a given mass, so which halos will be actually having the condition that the cooling time is smaller than the dynamical time? And you see as a function of redshift, basically, it's all the halos below 10 to the 12 solar mass, more or less. Now, the significance of that is that if you look at m star of the halo in the Schechter function, at high redshift, basically everything is more or less in a regime where cooling time is much smaller than the dynamical time. That again makes our whole problem much easier, because the gas, in the case that the cooling time is shorter than the dynamical time, will just collapse to the center of your halo on the dynamical time, which is the fastest time scale. So having said that, it seems that basically our problem set is actually one that is well defined, and we can hope that maybe based on first principles we can maybe learn a little bit more about galaxy formation, because the context seems so much easier than in later universe. Now, coming back to JWST, JWST seems really the natural choice to answer high redshift question. By high redshift I mean 6 and larger. And the 3 points that I would like to address in my talk today is, well, what can we say or what can we predict about Popfree star clusters and primeval galaxies? What can we say about reionization? And what can we say about seed black holes? Now, I should stress, JWST is really a unique instrument. And the last thing that we would like to do is more of the same. So there is no point in using JWST to basically redo what HSD is doing or what ground-based instruments are doing. And I think these 3 aspects have been highlighted many times as unique science opportunities with JWST. Now, what we did is we started off with a numerical project, which we called the Phoebe project, the first billion years project. And the idea in that project was that we wanted to bridge the mass gap between mini halos in which you form the first stars, all the way up to the first halos the first galaxies that you form in halos, right? And to do so, we used a version of the gadget code, which was used in the OLS project, but we added a number of physics to it. So we had, for example, molecular networks and cooling added. We added Popfree star formation, the evolution that yields from them. We seeded black holes from these Popfree stars, from the massive Popfree stars. We added dust from pan-stability supernova and AGB stars and type 2 supernova, and we actually also allowed that dust to be destroyed via thermal sputtering to just see what is your ratio of dust to metals. We included a Lyman-Werner background to see actually how molecular hydrogen is photodissociated by radiation, and we also included self-shielding against that radiation. And in post-processing, we coupled the simulations to simplex, which is a radiative transfer code. Now, the largest resolution simulation in box that we ran was an 8 megaparsec box, which had 2 times 1368 cube particles. So this was actually a box simulation that was quite heavy in terms of numerics. And the individual gas particle masses are around 1,000 solar masses that we had there. And here you see just a nice little movie of one of the more massive galaxies. And what's interesting, you see this is redshift 6, but you see there seems to be already kind of like a cold disk in that proto-galaxy with an old bulge, redshift 6. We ran a number of simulations with different setups, with different box sizes. We kept different numbers of particles, which resulted in different resolutions just to see what's happening. And we ran them down to various different redshifts. Again, this was mainly dictated by the amount of numerics and the amount of computing time we had. Now, one of the main things we wanted to achieve in these simulations was to make sure that we resolve the Jeans mass at the onset of molecular hydrogen formation. So when you reach roughly 1 particle per cubic centimeter, you start forming H2 molecules via the H- chain, all right? And if you want to resolve that more or less correctly, you want to make sure that at least your Jeans mass is resolved at that mass range. And this gray shaded area basically shows you that particle mass that you would need to achieve in terms of SPH particle mass to make sure that for typical Jeans masses, you resolve the Jeans mass with at least 100 SPH particles, around 100 SPH particles. Now, I'm showing you here also a compilation of recent non-zoom cosmological simulations in yellow symbols, and believe me, that's not on purpose so that you can't see the other people's work. That's just a mistake, maybe. But in any case, so what you see is, I guess there are a combination of the illustrious simulation, the Eagle, and also the Mufasa. I cannot actually tell you which one is which, but you see they're all in this regime. And the Phoebe simulations, the ones that we ran, are basically very complementary to those simulations. So obviously we can't reach those volumes, but we reach high resolution, and we can say something about basically bridging the mass gap and give us complementary information to what's going on here. Now, our simulations are not Zoom simulations. There have been a number of very interesting Zoom simulations, for example, the First Light simulation, which is happening here, or the Renaissance simulation. And again, our simulation project is very complementary to that because they give you basically a full box information of what's going on, in resolution being basically everywhere the same in the box. Now let's have a look into what we predict. So a first look obviously is a stellar mass function, if you like, and the symbols show you the different simulations that we ran. Now here the square is some observations, and so are the triangles, and the red line is a fit to the observations. Now I would say we are in fair agreement over the range that we actually simulate. So you can see, due to our resolution, in the highest resolution box, we go actually quite far down in mass, 10 to the 4, 10 to the 5. So I would not call it a galaxy, I would call it a clump. So one thing that is actually quite interesting is that if you look at, for example, here the fit from Duncan et al., and obviously we are not having large enough boxes to sample galaxies that massive, but in the range that we overlap in terms of mass, which you see here by the solid line, the fit to the observed data and our simulated data agree very well. Now what we then see here as a dashed line is the extrapolation by the observations from Duncan in terms of their Schechter mass function fit. And you see there they deviate quite significantly from ours. Now what we would argue, and what we argue actually, is that the reason for that is that because they're not going far enough down the faint end slope of their mass function to get a good enough estimate of the faint end slope. As a consequence, they're getting much steeper. And the reason they get much steeper is that they're just around m star. If you're around m star and fit your mass function, you always have a bias to getting a much steeper slope just because you're on the exponential tail. That's right, but this is again m star. We haven't put them up there. And there's obviously again reconstruction issues in terms of your lensing maps, etc., etc. But what they're finding is, and I'm not showing you here the UV one because they're getting just UV, right? Is also a little bit kind of like biased in terms of what kind of dust correction you assume, etc., etc. Even though you would argue low mass, low luminosity galaxies don't have much dust, but there's still dust correction you need to apply. So you cannot make a, let's say, self-consistent comparison between the both. That's what I'm saying. For stellar mass, it's much easier, while for UV luminosity, you have all these biases in there, right? Anyway, so now JWST will help us here by going below that. If they go and probe galaxies below m star in stellar mass, that will help us much more in getting a better estimate of the faint end slope. Okay, so this is one point where I think it will be very important. And what you see here is basically the alpha, the slope of the faint end slope that we find in our simulations versus some observational results. You see the error bars are huge and they're all over the place. And what we're finding is an increase from minus 1.5 to around minus 2, and then it becomes more or less constant at higher redshift, which you see here. But again, it will be very interesting because we will see galaxies here. Obviously not anything at m star or fainter than m star at redshift 10, looking with JWST. Now knowing that, you can go ahead and compare actually your halo to stellar mass relation. And here's the stellar mass versus the halo mass. This is the data from abundance matching by Beruzi and Silk at redshift 6, and that's the same data at redshift 8. So that's the same prediction at redshift 8. You see, this is our data. We have actually a quite large scatter in that relation. It's not a tight relation at all, right? And these are 1 sigma error bars you see here. And we maybe overpredict a little bit, but again, it could be a limited fitting range they have at redshift 6. Interestingly, at redshift 8 and above, their predictions are in very good agreement with what we find in our simulation. And this is just the universal baryon fraction here. Now, one thing I want you to take away from this plot is, and I'm happy to discuss if this can be real or not, is if you go to higher redshift, from 6 to 15, we basically don't find any change in that relation. They all lie on top of each other. If this is true, then again, JWST would give us an interesting insight into the growth of dark matter halos. If the relation between stellar mass, the average relation between stellar mass and dark matter halo mass is the same as a function of redshift, going from 6 upwards, then just by looking at the evolution of the stellar mass function, you will understand the evolution of the underlying dark matter halo mass function. And we can learn something about the growth of structure and dark matter at high redshift as well. Now, looking at star formation rate, and this is the star formation rate in mean sequence. Again, dots are our simulations and the other symbols are observations, redshift 6 all the way to redshift 11. And you see, well, one would say we're in fair agreement. So the slope that you see here put in is something where you basically have a slope of a power law slope of 0.9. All right? So it's not just linear, it's a little bit less than linear, sublinear. Now, a point I would like to raise. So you see often people showing you that and saying like, hey, great success, right? All done, we can go home. Well, is it really a great success? First of all, we have a quite large scatter. We would like to understand the scatter with respect to the observations, all right? But there's more to it. If you ask the observers, how did they derive star formation rates and stellar masses? They will tell you what they did is actually they assumed galaxies have an average age and then assumed a constant star formation rate for those galaxies. If you do that, by definition, you end up on a linear relation. Because if you say galaxies at a given redshift have the same average stellar age, then if you need to get some mass, you always end up more or less on the star formation rate, stellar mass relation, and it's a linear relation. If you look at these galaxies, and I will show you that in a second, none of them has a constant star formation rate. Now the question is, and this is a valid question, can we marginalize over the different varying star formation rates of galaxies and just come up with just one number and saying like, well, it's good enough to go for an average star formation rate with some kind of average age. Now here, a first clue to that answer, and batteries die on me today, maybe I need to get pointer version 1. So what you see is the star formation rate for galaxies more massive than 10 to the 7 solar masses, so more massive galaxies goes in this direction as a function of time. And what you see is, yes, indeed, we find increasing star formation histories, and this is something that many people find in their simulations. But the question is, does that mean that all galaxies move along these average star formation histories? Well, we can look into it, into individual galaxies, and you see, for example, here, small mass galaxies, more massive ones. You see, star formation histories are actually very stochastic. And the less massive you are, the more stochastic your star formation histories are indeed. So therefore, it is actually not clear that you can just go ahead and say it's a self-consistent comparison by saying, oh, we assume something that is a block with a certain average age and say, yes, this gives us what we should get from the observations. You can also ask yourself, so what is actually the baryon convergency efficiency? So what's the efficiency in converting baryons into stars as a function of halo mass? And what you can see here is, so these points, by the way, are observations by Megor et al. So we find a relation that increases with respect to halo mass, and the same is true with respect to stellar mass. So more massive galaxies, more massive halos are able to convert more of their stars, baryons into stars. Usually this is attributed to feedback being less efficient in driving out the material from these halos or stopping star formation in them. And you see actually, for galaxies at redshift 6, or any other redshift for that matter, that are around 10 to the 9 solar masses, roughly you manage to get 10% of the baryons into stars, right? This number is larger than the comparable number in the low redshift universe. Already, this seems to be an indication that if we look at redshift 6 and larger and see small mass galaxies, these are not necessarily the same objects we see today. Which is not a surprise if you live in a hierarchical universe, but it is a good question because you say, well, some of these might survive and get in this direction, especially if you look in the low redshift universe and find galaxies with very old stellar populations. I want to show you that even though I'm showing you here very tight relation, this is the 1 sigma error, deviation, and it's almost of the same order than the medians that I'm showing you here. So there's a huge scatter here as well. A fraction of that population is able to survive to today. From the simulation, or you mean observationally? Well, if you can get rotation, if you can get dynamical measures. No, this is redshift 0 for Megor et al. Yeah, so that's why I'm comparing. I'm saying redshift 0 data, we see larger baryon fractions, right, for Megor et al. And that's what we just find in our simulations. But if you believe it, there was a recent paper on ALMA data where they claimed, I think, they got some rotation curves. Anyway, now that's just general about a little bit about the properties of the galaxies. Now, coming back to primeval galaxies, how would we find them? Well, what we know about these is, well, primeval, by definition, we want them to have low metallicity and be very young in terms of their stellar ages. Now, you can look at the UV beta slope, which is basically a power law slope across basically 1,000 angstrom to 2,000 angstrom, and you can fit that nicely. And these are usually the bands that people use, and you can fit a nice power law to it. Now, if you do that, and I'm showing you here what you find in our simulations, just focus on the gray points, is that if you look at the UV-weighted age at redshift 5 for a bunch of galaxies in our simulations, the younger the UV-weighted age, the steeper the UV beta slope, so they're bluer. And the same is true if you look at the metallicity of the galaxies, so the less luminous, the younger and less metal-rich galaxy population is bluer. So what you want to do is, if you want to find these primeval galaxies, look at the UV beta slope, right? Now, what can we say about Popfree stars? I think the consensus is that we will not be able to see individual Popfree stars. But what can we say about Popfree star clusters? Are we able to see them, and what are their masses? So we looked into our simulation because we followed basically the formation of Popfree stars using our simulation having the resolution to resolve the mini halos in which they form. And here you see the stellar mass density as a function of redshift. These are for galaxies above certain masses, right? That's the overall one. Observational data agreement is quite good. Now this is here for the Popfree stars. One thing that you see immediately is around redshift 10 we seem to peak and then we seem to drop off. Reason for that is twofold. One is, in our simulation we assumed that Popfree stars follow a top-heavy IMF, basically from 25 solar mass to 500 solar mass. As a consequence, Popfree stars die off quite early on. They'll just live for a few million years before they die off. And therefore, if you don't produce enough new ones, this relation will just go down. So redshift 10 is basically a peak time during which you would see Popfree stars. Also, it will be probably the peak time during which you form Popfree star black hole remnants, all right? So this is the part when you would seed them or start seeding them. Now another very interesting thing is, if you look actually, let's say at redshift 10, you have more mass in Popfree stars than you have in galaxies more massive than 10 to the 8 solar masses. And the same is true at redshift 12 for 10 to the 7 solar masses. That doesn't mean that you will more easily see Popfree stars, because these Popfree stars actually are not large clusters, but they're in individual mini halos, while these galaxies are actually all the stars in one place. They're much more luminous, so you're much more likely to detect them than the Popfree stars. And why Popfree stars in simulations is important to take into account is shown here. So as an experiment, we ran a simulation in which we included Lyman-Werner background to basically destroy H2 molecules, and hence also destroy the formation of Popfree stars, because if you have no H2 molecules, you're not forming any stars in mini halos, because they're not able to, the gas is not able to cool. And we compared it to the same simulation without a Lyman-Werner background. So the yellow line is no Lyman-Werner background. If you look at the stellar mass as a function of redshift, you see initially, when you include Lyman-Werner radiation, the stellar mass is below the runs where you have no Lyman-Werner radiation, just because, well, if you have Lyman-Werner radiation, you don't allow Popfree stars to form, hence less star formation. If you go then to beyond redshift 10, all of a sudden, the stellar mass density basically increases in the runs where you include Lyman-Werner radiation. And the question is why? Well, if you allow for Popfree star formation, they form in mini halos. They live very shortly, they go off as pair instability supernova, they're able to blow out the gas and evacuate basically most of the gas from those mini halos, which is not available for further star formation later on. And that's why here, while initially, when the Lyman-Werner background is included, you stop Popfree star formation, later on you take over because this gas is available. It was never blown out by Popfree stars, and you can drive star formation more efficient because there's just more fuel available. And that's what you're seeing here in that trend. And the same trend can be seen by just looking at the amount of pristine gas and enriched gas, right? If you this is the ratio of gas mass in the runs with Lyman-Werner versus the divided by the run with no Lyman-Werner. So if you're below that, basically you have less enriched gas when you have no Lyman-Werner, right? Which makes sense because no Popfree stars forming, you're still below it. And you have lots more enriched gas, obviously, because no Popfree stars enriched, pristine gas because no Popfree stars enriched the gas. Now, what else can we say actually about Popfree star clusters? So there has been recently the claim by Zobralidal that they found an object called CR7, which is very Lyman alpha luminous. And they argued that this object is a prime candidate to be a Popfree star cluster. Now we said, okay, well, let's have a look into it. Let's make a simple theoretical argument. We know that if you have Lyman alpha photons, they are able also to impart momentum on the gas and actually drive a wind and insert feedback into the gas. Now you can basically work out the delicate balance between the feedback from Lyman alpha photons that are there for a given luminosity in a given halo, and ask yourself, when do you basically shut off any kind of star formation, or when is the luminosity from that Popfree star cluster so high that it basically stops any more star formation or any more Popfree star formation, and hence reducing the mass. And if you do that, you find basically that the stellar mass is a few times 10 to the 6 solar masses times the halo mass times some other factors, basically slight redshift dependence. Now, the important thing here to remember is, if you want to form a Popfree star cluster, you need to be in a halo that is not being previously enriched by any metals from previous star formation generations. So there is a natural limit to that mass mh, to the halo mass. It can, at max, be atomic cooling halo with no previous star formation. Because, by definition, if you wanted to have a star formation early on in it, it could be a smaller halo, but then the mass obviously would be much, much smaller. So the most massive mass that you can have here for a halo is the atomic cooling halo mass limit, which is around 10 to the 9-ish, right, with a redshift dependence. So therefore, the most massive mass that you can get is around 10 to the 6 solar mass for a Popfree star cluster, just due to the feedback from Lyman alpha photons. And the Lyman alpha luminosity is also limited due to that. And in our case, we assumed a top-heavy IMF for the Popfree stars. So to get basically a maximum boost from the Lyman alpha luminosity. And this is the range that we find as a function of redshift, allowable range. And that is much below CR7. So we would predict that CR7 is not a likely Popfree star cluster candidate. And in fact, people have found metal lines in Popfree which basically argue that there are metals, so this might not be really a Popfree star candidate. What else can we say about Popfree star formation and how the transition works? Well, in our simulations, what we find is that basically you always just find one generation of Popfree stars in a mini halo, then self-enrichment starts, and you no longer have any more Popfree star formation going on in the halos. And you start going to Pop2 star formation. But that's not all of the story. So what we did is we ran a zoom simulation, and this is the scale here, and you see metallicity and density of a halo, which is called halo A. And we looked at what happens actually when you have a supernova going off, and what happens to the metals, and how do they affect the neighborhood. So there's a halo just next to this halo, A. And what we see is that once the supernova goes off, the metals start getting distributed, you find actually metals all over the place. And in fact, we find that halos nearby get enriched by this one explosion. So the way that you actually shut down Popfree star formation is because you manage to enrich the neighborhood with metals and boost above a certain critical metallicity. The metallicity is very important for the gas fragmentation, and it basically regulates what are the smallest clumps that you can find in terms of mass. So if you have metals above a critical metallicity, people argue that then you transit to a Pop2 IMF, because now you are able to get smaller fragments. Now, as I said, in our simulations, we find basically that this is the main way of shutting down Popfree star formation in the neighborhood, having one halo going off and polluting the neighborhood.
Having the same type of simulations, it's a metallicity threshold as well, correct?
Sorry?
Between the two IMFs simulations, you use a fixed metallicity.
That's right. That's right.
10 to the minus 4.
Yes, we use that. It's debated, right? It's highly debated. But the interesting thing is, for the transition from Pop3 to Pop2, you can go up and down one order of magnitude in the metallicity. It doesn't change much. It changes the time scale by, we're really talking about tens of million years. So there's not big change in the overall results that I'm showing you here. All right, so what else can I say about metals, right? And that's again very important for high redshift galaxies. So we believe, well, as I told you, that cooling times are short. That means you feed galaxies very efficiently in halos at high redshifts. If this is the case, you would expect that there's always lots of primordial gas available to form stars, right? Now, we looked at redshift 6 at the distribution of star-forming gas in terms of its metallicity for a bunch of different galaxies. Now, what you can see is a few different interesting things. One is, well, yes, you find a tail going to low metallicities. This is basically the gas that comes in from the cosmic web is more or less primordial. However, you find also kind of like a peak around moderate high metallicities, almost solar. This is solar, right? 0. Here you almost have solar in this case, a bimodal distribution. Now that is a sign of self-enrichment, right? Previous star formation generations being able to self-enrich the gas. Now, if I tell you, look in the local universe at galaxies and stars, and let's say with Gaia, look at stars, and look at the metallicity distribution of those stars. Can we indeed find a pattern that resembles something like that? A range in metallicities for stars of a given age. That would be very interesting because it tells us something about how the formation process, the growth process of these galaxies really worked out. If you find really all all old stars are just at one metallicity with maybe a very narrow distribution, not showing a large tail, then you basically have shown that maybe this cold accretion is not as sufficient, or maybe there's something else going on, right, in feeding those galaxies. Here I'm just showing you as an example the gas phase metallicity for star-forming gas as a function of the star formation rate. So if you have high star formation rates, you have higher metallicities, and you can see these metallicities are actually significant given at redshift 6 for a galaxy that has just like 1 solar mass of stars forming per year. You're finding minus 0.5 in solar metallicity. Right? Again, this is implications for modeling observations, right? When you do model observations, usually people assume a single metallicity for your stellar population. And we would argue, well, you actually should not be doing that. Right? Now, what about element abundances? We know early on in the universe, at redshift 6, the universe is 1 billion years old, there was not much time for type 2 supernova actually to go off and provide lots of metals. And in fact, if you look at the element abundance in our simulation, this is the overall metallicity showing here, and this is just the metallicity in iron. Okay, if you just look in the metal mass in iron, you see that's clearly offset to the overall metallicity. All right? So our galaxies, or the stellar population in terms of the metallicities, don't have the solar ratios for alpha over iron. All right? And that's something you need to take into account. And here again, I show you that. So if you look at the total metallicity, this is the relation, and if you look at just in the iron metallicity, iron mass in metals, as a function of stellar mass, you see there's quite a big gap. So even for more massive galaxies, this gap becomes even larger. So one would want to take that actually into account again when you do stellar population modeling at high redshift. And the reason for that is very clear. It's just because the type 1s didn't have much time to go off, while the type 2s did. All right, so let me shift gear a little bit to reionization. So what can we say about reionization? Well, I mean, if you want to know if reionization is happening or not, all you can do is, what you can do easily is you just set up a simple differential equation. So the volume filling factor of ionized hydrogen, the change in it per time is basically whatever you produce in ionizing photons divided by the hydrogen number density, and minus whatever recombination rates you have in your gas, right? Which depends on the clumping factor of your gas. Now, so basically, when people now ask themselves, can we achieve reionization? What galaxies can we achieve reionization? The main uncertainties are really what is the number of ionizing photons that you get out from the underlying population, which includes the escape fraction. The other big uncertainty is obviously what's the clumping factor, but people usually assume a clumping factor, an average clumping factor, which can vary a little bit. Now, if you do that, you can ask yourself, let's go and look at the luminosity function, and we say, well, at 1600 angstroms, we know how to convert this luminosity to, let's say, the ionizing photon luminosity, and plot the ratio, plot that against the ratio of the clumping factor versus the escape fraction of stars, and ask ourselves how far down do we need to go in the luminosity function for a given slope of the luminosity function to achieve reionization. So if you have a high clumping factor or low escape fraction, so if you're in this regime, you see you need to go quite to very low magnitudes to achieve to get enough ionizing photons to achieve reionization. All right. Now, you see the main issue here again is where do we lie on this graph? Okay, what's the escape fraction of stars? And we said, well, okay, let's look into our simulation, do the post-processing. And this is a number of ionizing photons coming from galaxies or clumps or proto-galaxies with stellar masses below a certain limit, right? So blue is less than 10 to the 4, green is less than 10 to the 6, and red is less than 10 to the 8, all right? And as you can see, yes, it starts off with small mass galaxies, but then this is a log plot. Soon, more massive galaxies around redshift 80-ish, whatever, start taking over and producing all the ionizing photons that you need to keep the universe reionized or get the reionization going. Now, if you go and say, well, can we see them with JWST, and you can calculate basically the UV continuum luminosities, you see that these guys, which start off reionization really, are beyond what we can see with JWST. However, we can see most likely at minus 30 in AB magnitudes, the galaxies that are actually driving reionization, keeping reionization going at lower redshifts, okay? Responsible for finally getting reionization done. Anyway, so we tried to understand better escape fractions, right? And we said, okay, well, let's take our simulation. We had something like 70,000 galaxies. We did for 70,000 galaxies escape fraction calculations and got distributions. And we said like, yay, we get averages. So first we looked at the average and said, yeah, well, we see very nice trends, right? Here, for example, as halo mass, as a function of halo mass, different redshifts, what is the escape fraction, stellar mass, gas mass in those galaxies. Yeah, we find nice medians. However, if you look at the distribution, and that's shown here color-coded underneath it, and also already indicated by the error bars, the standard deviation, you see that's a wide distribution, all right? And the question is obviously, is that distribution so wide, can we still really work with just using the median, or do we really need to work with the distribution itself? And first, to get a better idea, we did a PCA analysis. These are the first three principal components. And what you see here on the bottom is every possible parameter we can come up with. So halo mass, stellar mass, gas mass, star formation rate, specific star formation rate, average age of stellar population, baryon fraction, stellar convergency fraction of baryons into stars, spin parameter of the halo. And you see, it doesn't seem that PCA is really telling us much. It seems there's no dominant PCA principal component that tells us how the escape fraction or what the main driver for the escape fraction is with respect to these parameters. That frustrated us a little bit, and then we said, okay, let's take a step back and think about it more physical. Well, what dominates is really the column density around sources that tells us how many photons can escape. And we looked at the column density, and what you're seeing here is the per halo average column density around each source within 10 parsec around each source, okay? So that's the column density around each stellar source within 10 parsec around it, okay? And what you see again is, well, and this is for all halos, here only halos where the stars are less than 5 million years, where you at least have one stellar particle that is younger than 5 million years, and here for all stellar particles needing to be older than 5 million years. And you see, yes, there seems to be a correlation that the higher your column density, average column density around star particles, star sources, the lower your escape fraction overall for that galaxy or the halo, from that halo. Which makes sense, right? If the gas is denser around sources, less photons come out. Again, you would argue, but I still find, like, you know, this quite large scatter. Then we said, well, okay, what if we look at the column density as a function of halo mass? And here it seemed to be really kind of like a more tight relation. So the reason that, for example, we're finding that the escape fraction on average or on median is lower for massive galaxies, as a function of redshift here shown, right? This is, for example, 10 to the 7 solar mass galaxy has lower escape fractions than a low mass galaxy. Is really shown here, the reason for it. If you look at the average column density as a function of halo mass, you find that it's higher in more massive halos. Reason being, deeper potential wells allow you to have much deeper column densities. And if you have deeper column densities, higher column densities, then the escape fraction just drops down, okay? So the physics is really indeed straightforward. You have lower escape fractions in more massive halos because the column density of gas around the sources in these halos is higher. Reason can be manifold. One is that your feedback is maybe not efficient enough to drive it out. Another reason is that the potential is deeper to bring the gas in deeper and make it denser. Now, coming back to the initial question is, well, how does the distribution of escape fractions then look? So what you see here is, as a function of redshift, for different halo masses, the halo mass is indicated here on the side, the escape fraction, all right? So let's start at high redshift. You see actually the distribution, and just focus on the gray histograms. The red histograms are only those for galaxies where at least one star particle is younger than 5 million years. So you see it's quite peaked initially, quite close to 1 for low mass halos. If you go and look at more massive halos, even at high redshifts, it's almost a flat distribution, all right? And it seems to be a systematic trend that if you go from more massive to lower, from low massive to more massive, that this distribution becomes flatter. And you see a similar trend going at lower redshifts, right? And here again, a very strong trend, right? Peaked here and then going flat. Now the important thing is really that you see it's a wide distribution. And these are all galaxies and halos of the same mass. So the takeaway message really is you cannot use one escape fraction to say this is the number I want to use to understand how reionization works. You cannot even go and just use the average, because the average as a function of halo mass is changing with redshift. You can go ahead obviously and try to use this distribution and fit that to halos and try to get a better idea of how reionization works. Now the important thing about it is all of that has consequences for the topology of how reionization is taking place. And that will be something that we hopefully will be able to test with SK and other observations. A final word about anisotropy. So you can ask yourself, well, okay, escape fraction is not one number if you average over a whole halo, but what about the direction? Is it at least the same in no matter what direction I look? And no, it's unfortunately not, right? So if you look here at the escape fraction, and this is just one is red, and blue is basically 0. You see here in a case with high escape fraction, you see lots comes out from one direction, very little from the other. And in this case, nothing comes out from the center, and most of it comes actually out from the outer part. So the topology from an individual source, again, is also very different. All right? All right, so I don't know how much I have, but I promised to talk about black holes. So let's talk quickly about black holes. So the high redshift universe obviously is the place where you see all these supermassive black holes that we hope to see. And there have been different channels discussed. One is where you, for example, have Popfree stars that just die off and you have a seed. Another one could be a stellar cluster and you have runaway mergers. And let me just go to this slide. Another one is direct collapse of gas via the stage or the stage of a supermassive star that collapses and forms a direct collapse seed black hole. Now the masses of these are in very different regions. So the Popfree remnants, they are around here, and this is actually age of the universe. The star clusters are here, and the direct collapse seed black holes are around these masses. So you can ask yourself, if I want to reach 10 to the 9 solar masses by redshift, redshift 6, which is 1 gigayear after the Big Bang, what Eddington factor do I need to grow them with to reach that mass? So for a Popfree star, a remnant of a few hundred solar masses, you actually need to run at Eddington from very early onwards all the way to up there, right? Obviously, you could exceed the Eddington limit and could potentially start at a later redshift. But if you say Eddington's my maximum, you really would need to start very early on. Now for star clusters, you could probably start much later, right? And for direct corpus black holes, you can actually start much, much later, right? So you have a head start using direct corpus black holes, and this is one of the reasons why people have been thinking about that as a seeding mechanism for supermassive black holes at redshift 6, right? 10 to the 9 solar mass black holes. Now one of the issues is, well, we find basically 1 per gigaparsec cube, all right? So therefore, people have been arguing that these seeds, they also need to be quite rare. You need to find them probably in high sigma fluctuation, density fluctuations in the universe, otherwise you would make too many. And therefore, kind of the standard paradigm is the most massive black holes you find in the high redshift universe are formed in the highest sigma fluctuation. Now I will argue that this is not necessarily the case. Before I do that, let me say a few things about the requirements for direct corpus black hole to happen. So what you want is you want to avoid star formation in halos when they're on their way from mini halos all the way to atomic cooling halos. The way to achieve that is via Lyman-Werner radiation, which basically is able to dissociate molecular hydrogen. And if you do that, what will happen is you basically have an isothermal collapse of gas, and this is an example of the temperature density relation of gas collapsing in a halo, which is a little bit below atomic cooling. But if you have basically a Lyman-Werner radiation there, you're not forming any molecules, which gives you this track, but you stay here and more or less go down isothermal to higher densities and have isothermal collapse a little bit at higher temperatures. But sorry? Oh yeah, angular momentum is obviously one of the big issues that people have been looking at, and people have been arguing about many different processes like turbulence, right? When they were discussing that, for example. There is something which you can still have. You can still have fragmentation happening in your disk, let's say, when you have angular momentum. And these fragments can still, on short time scales, merge, right? Which gives you a way around the angular momentum problem as well, right? Now, going down this route, so we ran a simulation using Lyman-Werner background and said to ourselves, okay, look, do we find any situations in which we find a formation site which is an atomic cooling halo, which is metal-free because there was no previous star formation, and which we had a Lyman-Werner background that is high enough to ensure that during the collapse, not at a very high stage when self-shielding becomes very efficient, you are forming H2 molecules. Now this level, well, this is work from 2014, is now gone upwards, so people are now actually arguing it should be larger, but still nevertheless, let me show you the results and actually point out what's the interesting point about it. Now here's a merger history of one of these halos where you find these conditions fulfilled. Now this is the main progenitor, and these are all the satellites that fall in. So you see the situation happens actually in the satellite and not in the most massive progenitor of a halo, all right? Happens at high redshift, and here you can see indicated by the cross is actually the halo in which it happens. And these are basically the sources that contribute to Lyman-Werner radiation. This is Lyman-Werner radiation contour. Now the interesting thing, again, an important thing is to realize it's not the main progenitor, but it's one of the satellites, right? Because you need a source that provides the Lyman-Werner radiation, okay? So, direct collapse black hole candidates, or halos, that form these direct collapse black holes are not high sigma fluctuations. This is the high sigma fluctuation. There are, however, some satellite galaxy, maybe in the vicinity of one of these, which is later accreted to them. That means you are actually potentially able to find them. You don't need to necessarily have a large survey because you want to capture high sigma fluctuations, but you can be potentially lucky in finding them even in smaller surveys where you don't have a large survey volume. Let me just say a final word. How would we find them? Search strategies, and this is actually work by Baska, who just sits up there. Now, you can say, well, okay, but if we know the star formation history, the Lyman-Werner if we know the SED of observed galaxy, all right? Let's say this is the observed galaxy. Then we can calculate the Lyman-Werner output, and we can calculate what would be the Lyman-Werner radiation at any given distance from an observed galaxy. Knowing that, you can basically make a J Lyman-Werner map. and pinpoint locations at which the Lyman-Werner radiation is above a critical value and say, do I find a direct collapse black hole there? And this figure here basically tells you that. So here, just as an example, you can say, okay, if I have a galaxy of, let's say, 10 to the 9 solar masses, and the average stellar age is 10 to the 7 years, what's the Lyman-Werner radiation? And you can see, am I critical or not? And these graded shaded contours are the critical levels. So you see, well, in this case, you would not be critical, but if the stellar population would be younger, let's say 6 million years on average, you would be in a critical regime. So you can do that and use that as a search strategy to find them, right? And since I'm running out of time, I'm pretty sure, let me put up the summary, which is way too much, way too long, but I've been trying to rush you through things that can happen in the first billion years. So the intrinsic scatter of the star formation rate main sequence increases towards low mass. I showed you the star formation rate, and I also showed you the star formation main sequence, so you saw there was a large scatter. So we should not assume a smooth increasing star formation rate or something that's even constant. That's just not at least physical in terms of what we see from the simulations. And the reason we see that in the simulations is obviously the growth of those halos, which is not always smooth, is the complex interplay between feedback as well. They're very stochastic in their nature. The metallicity of the star-forming ISM can be even in galaxies with star formation rates around 10 solar masses per year, can be even 0.5 solar. That's very high at redshift 6, all right? So you have pockets, but it is, again, important to realize, I'm not saying the average metallicity of those galaxies is 0.5 solar. That of the star-forming gas phase. Alpha elements, their abundance ratios are higher than what you see in the solar, what you get for the sun or in the solar neighborhood. At higher Z galaxies, again, something you need to take into account. Popfree star clusters are most likely never more massive than 10 to the 6 solar masses, which corresponds to something like 10 to the 43 ergs per second. If you look at Lyman alpha, again, that is depending to some extent on what your IMF is, but for top high IMF that we assume, this is what you get. Low mass galaxies drive reionization initially before more massive ones take over. The escape fraction is not just one number, all right? It is actually a number, and if you want to do a proper job, you want to use a distribution, try to model it. It is redshift dependent, it's viewing angle dependent, and shows a huge scatter. Direct Rayclaw formation is quite frequent, and it can explain the abundance of supermassive black holes at redshift 6 or larger. Close by sources do the job, and direct corpus black holes formed in satellites, right? They don't necessarily need to form in high sigma peaks. So this is a paradigm shift, right? Don't think of forming direct collapse or supermassive black holes in high sigma fluctuations. It can happen everywhere. It can happen to you too. All right, I would finish here. Thank you very much.
So thanks, Sadegh, for this very nice talk about the cosmic nerdery and galaxy formation and black hole formation. The podium is open for questions. Andrea, you're the first one. Wait.
How are you?
Thank you very much. About the last point, do direct collapse black hole form around high sigma peaks? So that's my question. Are those satellites of high sigma peaks? So then you're back to the problem of the large volume, or are there satellites of average galaxies?
So the answer would be they could, right? Because if you have a high, very luminous source, they could. Now there are a few things why I think it's not very likely. Reason is dust. Because if you have these very massive luminous sources, they probably have already pre-enriched with metals, etc., and they have dust. If they have dust, they're very, and you know the dust law basically becomes more and more, detonation becomes more and more important going down in the UV. So it will be quite important for the Lyman-Werner radiation. So they might actually not put out that much Lyman-Werner radiation, even though they obviously have a higher star formation rate, right? And would naturally, intrinsically produce more Lyman-Werner photons. So I guess the answer is it could happen, but it's quite unlikely because I think dust is going to destroy that game. And I have since I mentioned dust, Let me just show you a figure from dust, on dust. If I get there, see, I have all these extra slides. Oops, there we go. Well, what we can do in our simulations is say, okay, well, we look into our UV luminosity function that we get intrinsically and say, well, this is the observed one. What dust attenuation law do we need to empirically apply? And if you do that, you see the attenuation of 1500 as a function of stellar mass is actually quite steep. All right? Okay. And this the attenuation that we find basically powered the stellar mass 2.5. Okay? So therefore, we would naturally expect potentially less UV coming out.
Around the green. Thank you.
Hi, Sadegh. Great talk. So one potential tracer of Popfree is abundance ratios, not measured from galaxies in emission, because even getting a metallicity there is hard, but rather an absorption. And I was wondering, do your simulations track multiple species? And the reason why the abundance ratios are interesting is because, in principle, the record of Popfree can persist even after the Popfree stars are gone.
Yeah. So yes, we're tracing 11 elements. So in theory, we could. Now, one of the issues is when you say, well, after the Popfree is done, right? They could be there, but I mean, I would have always thought that quickly mixing it, etc., is going to happen, right? So how long they survive? Because from what I understand, your argument is to say, well, you still have them lingering around the element abundance ratios, maybe even frozen in the IGM, because if you blow the material out,
right,
not much is happening. Question is, well, first of all, you need to have something in the background to go through that, right? If you want to see an absorption, right? A source, right? Then you need to find a blob that is enriched just by the Popfree. So in theory, yes, but I'm not sure it's very likely. That's my answer. But we have it. We could do that if you want.
Next question to Volker.
Yeah, Sadegh, thanks. You showed that your baryon conversion efficiency in these high redshift galaxies is almost an order of magnitude larger than what we see in the present day universe. Well, it was a large fact in any case, but what makes you confident that the feedback physics you put in is actually producing galaxies in the present day universe that are realistic?
No, that's absolutely excellent question. So feedback is the main, well, as I would say, crux, right? So what we've done is, in a recent paper with Avery Mikeskin, we looked basically at the X-ray emission from feedback heated gas, right? So obviously in the local universe you have very good observations on X-ray heating from gas, X-ray emission from gas due to that heating. Now, so what he did was he used our outputs from the simulation, the feedback information we had, and compared it to those. So you can take them and just extrapolate the analytic work from low redshift to high redshift, all right? And compare what do the simulations give and what do you get from these analytic models, which are the super bubble model, super wind kind of models. And the interesting thing is that the X-ray emission that you get is comparable. It's actually quite okay agreement. This by itself is not 100% strong evidence that that means we're getting realistic galaxies at low redshifts. But it means, in terms of what we produce as observable X-ray emission from the gas affected by the feedback, is in somewhat in agreement with what you're seeing in the local universe. That's one line of evidence I would proceed. The other line of evidence, which is again very indirect, is to say, well, people have run the same kind of feedback model down to redshift 0 with the Eagle simulation suite. Obviously, they had a little bit of different physics in terms of the Popfree physics, etc., that we had in there, but it's the same Dalawecki and Shai feedback implementation, and they run it down to redshift 0, and they say,
except that if they apply that physics of this mass resolution that they're using, it doesn't work.
Well, see, this is exactly one of the problems. Now, again, what I would argue is to say, I agree with you, but it seemed for this comparison that we did for the X-rays, which is actually maybe an even more direct comparison, it's a first good step, right? But, I mean, I'm the first to throw my hands in the air to say feedback is the big problem, right? Subgrid modeling is the big problem.
Okay, I think I'm next here. Thanks, Sadegh. So given that you need the Lyman-Werner photons to make the direct collapse possible, could quasar formation trigger further quasar formation in the vicinity? Is that a possibility?
it could be a possibility, depending obviously on your spectra. You will have probably also a lot of X-rays coming out, which help then getting free electrons that help you getting into the H- channel, H- plus H. So yes, it could in principle help. Now the question is, if you have, let's say, these very luminous quasars, 10 to the 9 solar masses at redshift 6, which is 1 per gigaparsec. Yeah, but they're not going to make much damage, right? Because they're just, in terms of number density, so low. So I think it's still stellar sources that will have more impact in triggering this formation mechanism than quasar potentially.
So Daniel Severino?
Yes, I have a question about the stochasticity of star formation rates. You say that they are, so less massive galaxies are more stochastic, but does it depend on the resolution of the simulations? That's the
question. So we looked into that as well. So the less massive ones, I would argue, is the stochasticity is actually physical because of the feedback effects, right? They live really in these small halos. Now, resolution is definitely an issue because if you don't resolve much, then you just make one big star particle, right? And everything goes off, and feedback is obviously exaggerated over a very short time scale. And that was the reason why we, if I can get to that slide. This is the reason why we actually ran galaxies simulations with different mass resolution over and over. Okay, sorry, let me just do that first. You see, I was not trying to push you through all of that. So here we go. All right. So if you look at the level of scatter, all right, here. So the red dots are a summation with the highest resolution, and then the blue, then the black, then the light blue. Okay? So what you can see is the level of scatter, where let's say they overlap the blue and the red ones, is more or less the same, right? There's a factor of 10 difference in resolution, mass resolution, right? Between them. And even if you go to the black ones, you find the same level of scatter, right? A little bit larger scatter, again, I would argue that could be because we're actually now having a larger box, so we have a larger range of environments that contribute. But I would argue that in terms of resolution, we are more or less resolving it there. Right? Okay. And I mean, I can discuss it with you later even more so. What you really want to resolve is that your star formation rate, I mean, that you basically follow the lifetime of massive stars. So what you want to do is that given a certain star formation rate, you want to make sure that the conversion of one gas particle into a star particle happens on a time scale smaller than basically the age of your massive star. And this is for all our simulations basically satisfied. All right?
Well, hopefully a quick one. The direct collapse black holes, can they be observed? So not just that they are there and they're accreting, but so we can observe the collapse itself. So is there anything that people imagine that we could witness such an event eventually?
So the collapse itself, the formation of it itself, well, I mean, this goes back really to all the physics involved in direct or black hole formation, right? So one thing that one could think about, which is, do I give away the next paper idea? Well, I don't know. So one thing you could imagine is, if you have direct collapse black hole, right, that means you need to get a hell of a lot of baryons to the center of a dark matter halo, right? So if you need to do that, then what happens is, adiabatic contraction might actually steepen the profile of the dark matter halo in the center, right? Previously, before you actually form that black hole. Now, if you have basically dark matter that can self-annihilate, right? Self-interact, whatever, you can basically, based on the cross sections, maybe get a signal from that annihilation of the dark matter which was flowing inside, was coming along based on adiabatic contraction. This could be, for example, an signal. I mean, the other signals are always the same signals that people would discuss also for the formation of black holes, right? That you would see. Does that answer your question partially?
So maybe I can add 2 comments. Okay. So I think the dark matter annihilation will be trapped by the high density of the halo. We looked at that. Dominique Schleicher looked at that a few years ago. And I think you really need to blow away the original gas in order to see the enhanced annihilation rate pristine.
But here I'm arguing that you really, what you do is all of the gas goes basically into the black hole, right? If you say it starts in the atomic cooling halo, and really the large fraction of it really is used to make that direct collapse black hole, then maybe, but yes, obviously if gas is around, you will not get anything coming out. Dense gas.
Also the luminosity, I mean, these stars will be extremely puffed up. They will have radii of a few thousand solar radii. They will emit hardly any UV photons. They will be relatively cold on the surface. So I think UV or something will be the only one.
Yeah, I mean more thinking along the lines of gamma rays.
Yes, afterwards.
Hi, I'd like to ask another question about an effect you haven't covered so far, the so-called streaming velocities, so the offset velocities between baryons and dark matter. And since they cause a large effect on things like the baryon fraction, subsequently the minimum helium mass for star formation, and then potentially also for direct collapse black holes. So can you comment how this affects your results?
Right, so I think Umberto Maio has actually looked into that in quite extensively. So one thing for the Popfree, Pop2 transition, or even the onset of Popfree star formation, so he used a range of parameters which were reasonable at that time, and he found that it delays things in terms of when Popfree star formation sets in, obviously. But the delay didn't cause much change in the evolution of the galaxy population later. The reason, again, is these Popfree stars are actually not that large of a contribution to a galaxy. Even though for themselves, when they're in the mini halo, yes, they're the dominant source, but once they get incorporated in a larger galaxy, they are not really a large fraction of it. So a slight shift in when they form doesn't make much of a difference for the galaxy population at later times, talking redshift 6, etc. So he found that, right? And again, the same is true for direct collapse black holes, because we looked into what are the sources that most likely contribute those Lyman-Werner radiation, and it was not the Popfree stars. It was actually the Pop2 stars. Even though Popfree stars started early on, there was not much or enough coming from them to elevate the Lyman-Werner level to cause direct collapse. So it was really the Pop2 stars, which are again the later galaxies. Hence, a little change in initial Popfree star formation onset didn't make much of a difference. So the answer is, yes, it's there, it delays things a little bit, but it doesn't have much of an impact. That's at least what we found.
Because then it's easier to keep the surrounding pristine, because you're not forming many Pop3 stars, thus you don't spread metals, and subsequently it's easier for one halo to be pristine, only have H2 that is then destroyed by by Lyman-Werner radiation, and thus the black hole can form easier.
Yes, but you always still would need the Lyman-Werner background. That's the main thing. Because even if you say, I mean, your argument is absolutely correct, if you have the gas not yet being confined to a halo, it's not going to form any stars or form any molecules. But at a later time, when it gets confined, because that's when you want to make the direct collapse black hole, you still need to have something that kills the H2 during the collapse. Otherwise, you go into fragmentation, form stars, and not make a direct collapse.
So let me also maybe at the last question, it's about a small detail you mentioned. You showed the metallicity distribution of the gas and hence of the young stars, and you mentioned this should be taken into account when doing population synthesis models to interpret the light from high redshift observations of these galaxies. And I'm wondering why this is the case, because I would naively assume you're seeing mostly the light from the youngest population of stars, which per definition will be at the bulk of the metallicity, and you would not see much of the high metallicity tail. So which situation could you envision to actually make this tail observable? Because I could not come up with a method.
Well, I mean, let's go there. Where was it? So I showed you the way, I showed you a plot where I was trying to make the argument you can take the UV beta slope to look for primeval galaxies. And so what you see here is, again, the UV beta slope, right? And this is metallicity. So as you can see, there is kind of a still steep slope between it, right? So if you would be, I'm talking now about the local universe, not about the high redshift universe.
No, you mentioned in population synthesis of the high redshift universe,
Oh,
and you
right.
showed this skewed distribution, which peaked at -1, but it had a tail at -3, -4, and you mentioned this could be visible, and I could not really come up with a way to see that.
So this was not what I was trying to say. I was trying to say, if you go and look in the local universe and try to get a old population of stars and are able to get element ratios and metallicities, can we see something that represents basically what I see in the simulation happening?
Oh, I see,
30
yes.
times,
Okay.
right, and making the match. One thing is, obviously, at high redshift, this distribution that you see will be folded in and be in one of these points, and you're not able to say what contributed to it, because it's just too degenerate.
Yeah, and you would only see the most metal youngest population.
That's right, yeah. That's why I was referring to the local universe.
Yeah, okay. Good, I see no more hands up, so let's thank Sadegh again for this very nice talk.